Berlin, Germany, March 15, 1940. The morning sun filtered through the tall windows of the Reich Air Ministry building on Wilhelmstrasse, casting long shadows across tables covered with production reports, fuel specifications, and intelligence assessments. Oberst Friedrich Bergius, head of the Luftwaffe's Economic Analysis Division, placed his fountain pen on a report stamped Geheim, secret. The document's conclusion was clear, typed in precise German bureaucratic prose. American aviation fuel production poses no strategic threat to Reich air superiority for the foreseeable future. What Bergius couldn't know, what none of them could know, was that he was reading his own service's death warrant. The Luftwaffe's economists had done their homework. Or so they believed. Their intelligence indicated that American refineries were producing aviation gasoline at approximately 87-octane rating, adequate for civilian aircraft but decidedly inferior to Germany's own synthetic fuel program. The numbers seemed to support their confidence. In 1939, Germany produced 72,000 metric tons of aviation fuel per month through the revolutionary Fischer-Tropsch process, synthesizing fuel from coal. The United States, despite its vast petroleum reserves, appeared to be producing aviation gasoline of lower quality and in quantities that posed no immediate concern. The Americans, Bergius remarked to his deputy, Hauptmann Werner Plieger, according to post-war testimony, are wealthy in crude petroleum but poor in chemical expertise. Their refineries are designed for automotive gasoline, not aviation fuel. They lack our synthetic capabilities. The report sitting on Bergius's desk contained detailed analysis. American refineries used primarily thermal cracking methods, producing fuel with octane ratings between 73 and 87. The document noted that while the United States possessed theoretical refining capacity of approximately 4.5 million barrels per day, less than 2% of this output could be converted to aviation-grade gasoline. The conclusion appeared mathematically sound. Even if America entered the war, their fuel production could not support a strategic bombing campaign while simultaneously supplying Britain and maintaining their own minimal air force. The Luftwaffe's confidence rested on hard technical facts. German aircraft engines, particularly the Daimler-Benz DB601 and the BMW 801, were designed to run on 87-octane B4 fuel, occasionally boosted with MW-50 methanol water injection for short periods of emergency power. These engines produced impressive specifications. The DB601A generated 1,175 horsepower at 2,400 revolutions per minute, sufficient to propel the Bf-109E to 570 km per hour. Intelligence reports indicated that British Spitfires and Hurricanes used similar 87-octane fuel, occasionally 100 octane in limited quantities for testing purposes only. The British, a Luftwaffe intelligence assessment from April 1940 stated, possess perhaps 2,000 tons of 100-octane fuel, sufficient for experimental purposes but not operational deployment. Production capacity in the United Kingdom for high-octane aviation fuel is severely limited by the catalytic cracking technology required, which the British do not possess in scale. What the report failed to mention, what German intelligence had catastrophically missed, was the single line buried in a U.S. Army Air Corps procurement document from June 1938, standard fuel specification revised to 100-octane minimum for all pursuit aircraft, effective January 1940. The Economists had modeled American fuel production using 1937 data. They had calculated refining capacity based on thermal cracking technology. They had estimated strategic reserves based on peacetime consumption patterns. Every calculation was precise, every assumption was logical, every conclusion was defensible. Every single number was wrong. In the spring of 1940, as Bergius signed his report certifying German air superiority for the next 3 years minimum, a very different reality was unfolding across the Atlantic. At refineries in Texas, California, and Louisiana, a new technology was coming online. Catalytic cracking using aluminosilicate catalysts, capable of producing high-octane aviation gasoline in unprecedented quantities. At the Humble Oil Refinery in Baytown, Texas, engineers had just completed installation of the Houdry process units, capable of producing 100-octane fuel at a rate of 15,000 barrels per day from a single facility. But the Luftwaffe's economists weren't tracking the Houdry process. They weren't monitoring American patents for catalytic cracking. They weren't paying attention to a seemingly minor detail. In 1939, the United States had produced exactly 40,000 barrels of 100-octane aviation gasoline. In 1940, that number would reach 165,000 barrels. By 1941, it would exceed 1.2 million barrels. The transformation had already begun. The Luftwaffe just didn't know it yet. German confidence in fuel superiority extended beyond mere production statistics. The technical specifications seemed to support their position. The Bf 109 times 10 to the power of -3, the standard Luftwaffe fighter in 1940, carried 400 liters of fuel internally, providing approximately 90 minutes of combat endurance. The aircraft's DB601A engine could sustain 1,175 horsepower continuously, with brief emergency boosts to 1,270 horsepower using MW50 injection. These specifications were considered more than adequate for defensive operations over Germany and offensive operations over Britain, given the short distances involved. Our fuel allows for 30 minutes of combat at full power, a Luftwaffe training manual from 1940 explained. British fighters, operating with similar fuel, face identical limitations. The decisive factor will be pilot skill and aircraft numbers, not fuel chemistry. The manual was already obsolete when it was printed. Reichsmarschall Hermann Göring, Commander-in-Chief of the Luftwaffe, reviewed the fuel assessment in April 1940 with characteristic confidence. The Americans, he told his staff during a meeting at Carenhall, his estate outside Berlin, cannot challenge German air power. They lack the industrial capacity for sustained air warfare. Their fuel production is adequate for commercial aviation, nothing more. The meeting notes, recovered after the war, show that not a single officer questioned this assessment. The numbers supported it. The intelligence confirmed it. The technical specifications validated it. Within 4 years, Göring would be begging his own engineers to explain how American aircraft were flying missions that should have been thermodynamically impossible. RAF Duxford, England. September 7, 1940. Flight Lieutenant Brian Lane of No. 19 Squadron climbed out of his Spitfire Mki with hands that wouldn't stop shaking. His ground crew noticed immediately. Lane was a veteran pilot with 15 kills, not someone who rattled easily. But the engagement over the Thames estuary that afternoon had been different. Very different. "I pushed the boost lever through the gate," Lane reported in his combat debriefing, later preserved in RAF records. Expected the usual surge to 6 pounds boost, perhaps 1,300 horsepower for 30 seconds before overheating. But the Merlin kept pulling. 7 pounds. 8 pounds. 9 pounds. The engine note changed, higher, sharper, almost angry. The Jerry Messerschmitt I was chasing. He couldn't believe it. Neither could I. I stayed at full emergency power for nearly 2 full minutes. The engine temperature climbed but held. When I broke off, my fuel was low, but the engine was intact. Lane had just experienced his first combat sortie using 100-octane fuel. The transition had happened quietly. In August 1940, with the Battle of Britain reaching its crescendo, RAF Fighter Command had received the first large-scale shipments of 100-octane aviation gasoline from American refineries. The fuel arrived in 50-gallon drums marked simply 100/130, indicating 100-octane rating for lean mixture operation, 130-octane for rich mixture with full supercharger boost. Ground crews were given minimal briefing. Use it exactly like 87-octane, but pilots could push emergency power longer if needed. What nobody had fully explained was the thermodynamic revolution contained in those drums. The Rolls-Royce Merlin 3 engine in Lane's Spitfire was designed for 87-octane fuel, with a compression ratio of 6:1 and a maximum boost pressure of 6 pounds per square inch, generating 1,030 horsepower for takeoff. With 100-octane fuel, the same engine could sustain 9 pounds of boost, or briefly, 12 pounds, without detonation. The result was staggering. Emergency power jumped from 1,030 horsepower to 1,310 horsepower, a 27% increase in thrust from the same engine, the same airframe, the same pilot. But it was the sustained duration that changed everything. On 87-octane fuel, a Spitfire pilot could use emergency power for perhaps 30 seconds before cylinder head temperatures reached critical levels, risking engine damage or failure. On 100-octane, that duration extended to 5 minutes or more. In a dogfight lasting 10 to 15 minutes, that meant the difference between one brief acceleration advantage and sustained superiority throughout the entire engagement. Luftwaffe pilots noticed immediately. Hauptmann Helmut Wick, one of Germany's highest-scoring aces with 42 victories, reported on September 15, 1940, now commemorated as Battle of Britain Day, the Spitfires today fought differently. More aggressive. They pursued at full power for much longer than previously observed. Our standard evasion tactics, full throttle climb to force fuel exhaustion, proved ineffective. Several Spitfires maintained pursuit through climbs exceeding 3,000 meters altitude gain. This should not be possible with their fuel reserves. Wick's combat report reached Luftwaffe intelligence, where analysts dismissed it as pilot exaggeration under combat stress. The technical impossibility was clear. British fuel specifications indicated 87 octane, identical to German standards. The Merlin engine specifications confirmed it couldn't sustain high boost pressure on 87 octane without catastrophic detonation. Therefore, Wick must have been mistaken. The numbers said it was impossible. The pilots were reporting it anyway. By October 1940, the pattern was undeniable. Luftwaffe combat loss reports showed a disturbing trend. Messerschmitt Bf 109E fighters, previously holding slight performance advantages over Spitfires at most altitudes, were increasingly being caught and destroyed during pursuits that should have been successful escapes. The Bf 109E could reach 560 km per hour at 4,000 meters altitude, slightly faster than the Spitfire Mki's 545 km per hour. But combat reports indicated Spitfires were somehow matching or exceeding these speeds in sustained chases. It defies the specifications, an intelligence report from Luftwaffe 2 headquarters stated on October 28, 1940. Either British aircraft performance has been significantly underestimated, or they have made undisclosed engine modifications. Request Technical Intelligence prioritize this discrepancy. The answer was simpler than anyone imagined. The British hadn't modified the engines. They had simply filled the tanks with better fuel. What the Luftwaffe intelligence officers couldn't see, couldn't even conceive of, was the industrial mobilization occurring across the Atlantic. By October 1940, American refineries were producing 100-octane aviation gasoline at a rate of 40,000 barrels per day. The Humble oil refinery in Baytown had expanded to 18,000 barrels daily capacity. Shell Oil's Martinez, California facility added 12,000 barrels per day. Standard Oil of New Jersey brought online 3 new catalytic cracking units, each producing 8,000 barrels daily. The production curve was exponential, but German intelligence was still using linear projections. The chemistry itself represented a quantum leap. Traditional 87-octane fuel consisted primarily of straight-chain hydrocarbons, N-heptane mixed with iso-octane in an 87:13 ratio, with small amounts of tetraethyl lead as an anti-knock additive. The fuel worked adequately at low compression ratios but would pre-detonate, knock, under high pressure and temperature, destroying engines within minutes. 100-octane fuel used a fundamentally different hydrocarbon structure, primarily branched-chain isoparaffins, produced through catalytic cracking and alkylation processes. The molecular structure of iso-octane, 2,2,4-trimethylpentane, resisted compression ignition far better than straight-chain molecules. Adding 4 to 6 milliliters of tetraethyl lead per gallon increased the effective octane rating to 130 under rich mixture conditions. The result, An engine could compress the fuel mixture to much higher pressures, extracting more power per explosion, without pre-ignition destroying the cylinder. For pilots, this translated to a simple reality. Push the throttle forward, and the engine delivered. Not for 30 seconds. For as long as the fuel lasted. Lieutenant Commander James Thatch of the U.S. Navy, testing the F-4F Wildcat fighter with 100-octane fuel in November 1940, reported, "The Wright R-1830 engine develops 1,200 horsepower at full military power on 100 octane, compared to 1,000 horsepower on 87 octane. But the critical difference is sustainability. On 87 octane, we could maintain full power for perhaps 1 minute before oil temperature forced throttle reduction. On 100 octane, full power is sustainable for the entire combat engagement, limited only by fuel quantity, not engine temperature. This transforms tactics entirely." Thatch's report circulated through U.S. Navy aviation bureaus but never reached German intelligence. By December 1940, RAF Fighter Command was fully converted to 100-octane fuel. Every Spitfire, every Hurricane, every Bristol Beaufighter received the new fuel as standard. Maintenance reports showed a curious trend. Engine overhaul intervals actually increased slightly, despite the higher power settings. The fuel burned cleaner, left fewer deposits, and produced less corrosive combustion byproducts than 87 octane. In Berlin, Oberst Bergius reviewed the latest intelligence summaries with growing confusion. British fighter production was increasing. That was expected. Pilot training was intensifying. Also expected. But combat performance reports indicated capabilities that shouldn't exist with known British fuel specifications. "Request technical assessment," Bergius wrote in a memo dated January 4, 1941. British aircraft appear to exceed published performance specifications by significant margins. Possible explanations: 1. Specifications were deliberately understated for security purposes. 2. Undisclosed engine modifications. 3. Superior pilot training producing better results with equivalent equipment. Recommend captured British aircraft be tested with Reich fuel to establish baseline comparisons. Option 4, that the fuel itself had changed, never appeared on the list. The captured aircraft tests were conducted in February 1941 at the Luftwaffe's test facility at Rechlin. A Spitfire MKIIA, forced down intact in France, was fueled with German 87-octane B4 fuel and flown by Luftwaffe test pilots. The results matched published British specifications almost exactly. 5,900 feet per minute maximum climb rate, 370 miles per hour maximum speed at 19,000 feet, approximately 90 minutes endurance at combat power. British specifications confirmed accurate, the test report concluded. No evidence of performance enhancements beyond published data. Combat reports of superior performance likely reflect pilot skill differential and tactical advantages of defensive operations. The test pilots had proven what everyone already believed. The Spitfire, on 87-octane fuel, performed exactly as designed. Nobody thought to test it with 100 octane. Schweinfurt, Germany. October 14, 1943. The industrial city of Schweinfurt, 200 miles deep into German territory, produced 42% of Nazi Germany's ball bearings, precision components essential for tanks, aircraft, and virtually every piece of military machinery. On this Thursday afternoon, it was about to receive its second visit from the U.S. 8th Air Force in less than 3 months. The first raid, on August 17th, had cost the Americans 36 B-17 Flying Fortress bombers out of 230 dispatched. The Luftwaffe had won that battle. Today would be different. Today, the escorts would reach Schweinfurt. At 1,340 hours, Oberleutnant Heinz Nock of Jagdgeschwader 11 spotted the first American formation at 27,000 feet altitude. 291 B-17 bombers in tight combat box formations, their contrails stretching 40 miles across the sky. It should have been a slaughter. The American bombers had taken off from England without fighter escort. No Allied fighter possessed the range to accompany bombers to Schweinfurt and return. The Luftwaffe had 300 fighters positioned along the route. Bf-109GS, FW-190A-8S, even twin-engine Bf-110G destroyer aircraft armed with 30mm cannons for long-range bomber interception. But as Noakes' swarm formation dove toward the bomber stream, something appeared that shouldn't exist. Indianer. Indianer. The warning call crackled across Luftwaffe radio frequencies, the code word for American fighters. Impossible. The P-47 Thunderbolts that escorted the bombers to the German border had turned back 30 minutes ago, their fuel exhausted. No Allied fighter could reach this deep into Germany. Except there they were. The aircraft were P-51B Mustangs, painted in the distinctive olive drab and gray of the U.S. Army Air Forces, drop tanks still attached to their wings. They had taken off from English bases 520 miles away. They had escorted the bombers across the North Sea, across Belgium, across the Rhine, into the industrial heart of Germany. And they still had fuel to fight. The thermodynamic impossibility of their presence could be calculated precisely. AP-51B carried 184 gallons of internal fuel in its fuselage tanks. At normal cruise power, 1,700 revolutions per minute, 30 inches manifold pressure, the Packard-built Merlin V-1650-3 engine consumed approximately 65 gallons per hour. The flight from England to Schweinfurt required 2.5 hours, consuming 162.5 gallons. That left 21.5 gallons, enough for perhaps 12 minutes of cruise flight or 5 minutes of combat power. But the P-51BS over Schweinfurt carried two 75-gallon drop tanks, adding 150 gallons of external fuel capacity. Even accounting for the fuel consumed, they arrived over Schweinfurt with 45 to 50 gallons remaining in their internal tanks. At combat power settings, 3,000 revolutions per minute, 61 inches manifold pressure, the Merlin could burn 125 gallons per hour, providing approximately 22 minutes of full combat power. 22 minutes. Over Schweinfurt. 200 miles inside Germany. It was, quite literally, impossible according to every calculation the Luftwaffe had made about American strategic capabilities. The combat was brutal and decisive. The P-51BS, burning 100-octane fuel at 61 inches manifold pressure, generated 1,650 horsepower from engines designed for 1,380 horsepower maximum. This wasn't emergency power to be used for 30 seconds and then reduced. This was sustained combat power, maintainable for the entire engagement. The Mustangs accelerated to 440 miles per hour in level flight, climbed at 3,500 feet per minute, and turned inside the German fighters with energy to spare. Heinz Noack, who survived the engagement, later wrote in his diary, "The Mustangs fought with a fury and persistence we had not encountered before. They pursued at full power for the entire combat, perhaps 15 minutes of continuous high-speed maneuvering. Our own aircraft, after 5 to 6 minutes at emergency power, must reduce throttle or risk engine damage. The Americans never reduced throttle. They never had to." The Schweinfurt raid cost the U.S. 8th Air Force 60 B-17s shot down, a devastating 20.5% loss rate that would temporarily halt daylight strategic bombing. But it cost the Luftwaffe something more precious, their defensive strategy. Every calculation about maximum fighter escort range, every tactical plan based on creating a fighter-free zone deep inside Germany, every assumption about the impossibility of sustained American air superiority over the Reich, all of it collapsed in the skies over Schweinfurt. The Americans had solved the fuel equation. The Luftwaffe was only beginning to understand what that meant. In November 1943, German intelligence finally obtained a sample of American aviation fuel from a crashed P-47 Thunderbolt in occupied France. The fuel was sent to the Technische Hochschule in Berlin for analysis. The chemist's report, dated November 28, 1943, landed on Oberst Bergius's desk like a bomb. Sample analysis reveals octane rating of 100, significantly exceeding previous intelligence estimates of 87 octane. Fuel composition indicates advanced catalytic cracking processes producing high concentrations of ISO paraffins. Tetraethyl lead content, 4.6 milliliters per gallon, double Reich standard. Performance number under rich mixture conditions, 130. Assessment. This fuel permits engine operation at boost pressures and power settings impossible with Reich B4 fuel. Recommended immediate investigation of American fuel production capacity and distribution infrastructure. Bergius requested an emergency meeting of the Luftwaffe Economic Analysis Division. The question was simple. How much of this fuel could the Americans actually produce? The answer, when it arrived in January 1944, was staggering. American 100-octane production had reached 514,000 barrels per day, approximately 21.6 million gallons daily. To put this in context, the entire German aviation fuel production, synthetic and petroleum-based combined, totaled approximately 175,000 barrels per day, of which less than 20% was 87-octane aviation grade, the rest being lower-grade fuel for training aircraft and transport planes. The Americans were producing 3 times Germany's total aviation fuel output, and all of it was higher quality. But the production figures were only the beginning of the strategic nightmare. The Americans had distributed this fuel across a global network. England received 200,000 barrels per day via tanker convoy. North Africa received 45,000 barrels per day through Mediterranean shipping. China received 15,000 barrels per day via the hump airlift over the Himalayas. Australia received 35,000 barrels per day through Pacific supply lines. Even the Soviet Union, via Lend-Lease, received 55,000 barrels per day through Murmansk convoys and Persian Gulf routes. Every Allied aircraft, on every front, flew on 100-octane fuel. Every German aircraft flew on 87-octane or lower. Generalleutnant Adolf Galland, Inspector General of Fighters, reviewed the intelligence assessment with cold fury. In a meeting at Luftwaffe High Command on February 12, 1944, he stated bluntly, "Gentlemen, we are fighting an enemy who can operate their engines at power settings that would destroy ours within minutes. They can sustain combat performance for entire missions while we must carefully ration our emergency power. They can climb higher, fight longer, and return home with fuel to spare. This is not a tactical problem. This is a strategic impossibility we are being asked to overcome with tactics." The room was silent. Everyone understood what Galland was saying. The Luftwaffe was being asked to win an air war with one hand tied behind its back, fighting against an enemy whose aircraft had a fundamental, insurmountable advantage built into their fuel tanks. The economic analysis became more granular and more disturbing. In 1944, the United States produced 85 million barrels of 100-octane aviation gasoline, enough to fuel 333,000 fighter sorties per month, assuming 255 gallons per sortie for AP-51 escort mission. Germany's entire 1944 aviation fuel production, approximately 64 million barrels of all grades combined, could fuel approximately 185,000 fighter sorties per month at similar consumption rates. But Germany had to fuel fighters, bombers, trainers, transports, and reconnaissance aircraft from that 64 million barrels. The Americans had 85 million barrels of 100-octane just for fighters and bombers, plus additional lower-grade fuel for training and transport. The industrial disparity was crushing. The Sun Oil Company's Marcus Hook, Pennsylvania refinery alone produced 25,000 barrels per day of 100-octane fuel, more than the entire Austrian petroleum industry's total output of all fuel grades combined. The Standard Oil of New Jersey refineries at Baton Rouge produced 45,000 barrels per day. The Shell refineries at Houston produced 38,000 barrels per day. By mid-1944, American refineries had built so much excess capacity that they were producing 100-octane fuel faster than the Army Air Forces could consume it. Strategic reserves grew to 150 million barrels by December 1944, enough to fuel every American aircraft in every theater for 6 months of intensive operations without producing another gallon. Germany, meanwhile, was rationing fuel so severely that pilot training had been cut to 110 flight hours before combat deployment, compared to 225 hours for American pilots. New pilots arrived at operational units having never flown at full military power for more than 30 seconds. They faced American pilots who had hundreds of hours at full power, because their training fuel was the same 100 octane their combat fuel would be. In April 1944, the Luftwaffe conducted a desperate experiment. Engineers developed a high-octane fuel additive designated MW50, a mixture of 50% methanol and 50% water, injected directly into the engine manifold during emergency power settings. The evaporating methanol-water mixture cooled the combustion chamber, allowing brief periods of increased boost pressure without detonation. The system worked, but only for 10-minute bursts before the MW50 tank emptied. American pilots using 100 octane didn't need MW50. They just pushed the throttle forward and left it there. By summer 1944, the strategic bombing campaign had achieved what ground offensives could not: the systematic destruction of German synthetic fuel plants. The Luna synthetic fuel complex, bombed on May 12, 1944, produced 300,000 tons annually, nearly 20% of German aviation fuel. It was hit by 2,000 tons of bombs delivered by B-17s, escorted by P-51s burning 100 octane fuel for a 1,200-mile round-trip mission that included 45 minutes over the target. The Luna raid required American aircraft to carry 142,000 gallons of 100 octane fuel. The Germans could not have fueled an equivalent strike force even if they had possessed the aircraft and crews. The mathematics are inescapable, a Luftwaffe quartermaster report from June 1944 concluded. The Americans possess fuel superiority of approximately 4:1 in quantity and unmeasurable superiority in quality. They can afford to train pilots longer, operate engines harder, and sustain combat power indefinitely. We cannot match this disparity through tactical innovation or pilot courage. This is a question of chemistry and industrial capacity, and we have lost both competitions decisively. Adolf Galland, in his post-war interrogation, put it more bluntly: "Give me 100 octane fuel and I'll give you the Me-262 jet fighter 6 months earlier. Give me American fuel production capacity and I'll give you air superiority over Berlin. But give me German fuel to fight American fuel, and I'll give you exactly what happened: defeat in the air, followed by defeat on the ground."